I'm Ben Berger, and this is a joint work with a bunch of teammates at Offchain Labs. And today I'm going to tell you about BoLD, which is the next generation dispute resolution protocol for Arbitrum. So let me start with a very, very oversimplified background on layer 2 blockchains. So a layer 2 blockchain is a scaling solution that aims to solve the limited throughput problem that layer 1 blockchains such as Ethereum suffer from. And so a layer 2 blockchain, like a bunch of other blockchains, will receive and process a list of transactions, and this will in turn update the state of the layer 2 blockchain. And every once in a while, say once per hour, the current state of the L2 will be posted onto a proving protocol on the underlying L1 blockchain with the aim of convincing the L1 that this state is really the true result of the computation. And so the idea here is to increase the limited throughput of Ethereum by by offloading the expensive computation off of Ethereum, and instead using Ethereum just to record and verify that the computation went correctly. So just as a very naive example, these bottom rectangles in this picture, these are the intermediate states resulting from the computation of these subsequences of transactions, and only they will be posted and proven onto Ethereum, again, say once per hour. So the layer one, the layer one can be any layer one. So, but imagine Ethereum for now. Okay. Okay, and of course, the challenge that layer two, that such a system needs to solve, is how to convince, say, Ethereum that this posted state is valid. And ideally, we would like to be able to do this proof or conviction in a permissionless way, meaning that we want anyone to be able to participate and post and prove such an assertion without compromising the security of the system. And so today, there are two main approaches for doing this. There's the ZK rollup approach, which was discussed today already. And Arbitrum is in the other approach, which is called the optimistic approach. And under this approach, the checkpoint state is posted onto the L1 on its own, alone, and it will be considered valid unless it is challenged by a conflicting claim within some predetermined deadline. And if such a challenge happens, then optimistic rollups solve the conflict using a dispute resolution protocol, which is really a set of smart contracts on the L1, which allow these conflicting assertions to compete with each other. Okay, so now I want to briefly go over the current dispute resolution protocol that runs on Arbitrum, and I will be very oversimplifying again, but I hope that the main ideas come through. And in particular, I'm going to focus just on the confirmation of a single checkpoint state and not worry about how to combine all these checkpoint states together, which is also interesting. So for the sake of this presentation, let's assume that S0 is the last L2 checkpoint state that was already confirmed on the L1. And now the current goal is to confirm the next checkpoint state, which is obtained from S0 after the L2 has executed the next n computation steps. And so what happens now is that the participants, whoever wants to participate, which we call validators in this context, what they need to do to participate is propose an assertion for the final state, and they need to lock some stake, which will be confiscated from them if they lose in this contest. So as an example, imagine that we have 4 participants. Here, 2 validators stake on the correct assertion SN, and 2 other validators also join and stake on other 2 assertions. And to emphasize, the goal of the adversary here is to get the wrong state to be confirmed. Okay, so now after the participants have been established, there's some way that the protocol sort of arranges 1 versus 1 games between them and there's a way to orchestrate these games, which I will not go into. But I do want to go into how how each of these games look like. So the 1 versus 1 games goes by, so the 2 players take turns making moves, and the protocol maintains chess clocks for both players for making these moves. And now in each round of this game, the parties implicitly agree on the start state, but disagree on the end state. And at every round, they reduce the distance between the start and the end state by proposing their implicitly proposing the midpoint state that they think is the correct midpoint state. So after a logarithmic in n number of rounds, the dispute will reduce to a single computation step, in which case the L1 smart contract itself will execute that computation step starting from the ST here to determine which one of them is correct. And so I didn't mention that the time that this chess clock is initialized to is called, we call it the challenge period. So there are two straightforward observations to make from the story I just told you. First thing that should be pretty clear is that an honest party that executes all the correct moves can force victory in this game. But very importantly, this is assuming that this challenge period is long enough to allow sufficient time for the honest party to calculate, submit, and process all these moves, considering the potential censorship attacks that his move just might not get onto the L1 smart contract. And so today, there is a social consensus that censorship cannot go on for more than a week without a proper response from the community. So in practice, the challenge period today on the current protocol is set to about 1 week. And the second observation is that a malicious party can start by staking on the correct end state, but still lose on purpose, say in this game, in the middle, proposing the wrong endpoint state. Okay, so this was the current protocol, and it has very desirable properties. In particular, it satisfies very strong safety, liveness, and incentive guarantees, but it has some very difficult, very bad drawbacks. So the first one is that all honest validators that have interest in the security of the chain must participate and stake independently. And this is because if I'm an honest validator and I see that another party has already staked on the correct end state, I cannot be sure that they won't turn out to be malicious. So I have to participate, and I cannot trust anybody but myself. And second, delay attacks are possible here. And I'm not going to go into how such an attack goes, but it is the case that if an adversary is willing to sacrifice n stakes, then it can cause the protocol to delay by a factor of n. Okay, so this brings me finally to the new protocol, BoLD. And I'm just going to go over the main ideas due to the lack of time. So BoLD will still implement a bisection style game like I described, but it does so in different but important ways. And so the single main important idea that BoLD introduces is what's called an history commitment. So instead of just staking and proposing the end state to the protocol, players will instead stake on a commitment to the entire state sequence S0 to Sn. And this is done by posting the root of a Merkle tree that encodes this sequence. And so I'm not going to go into details, but I hope you can imagine that how once anyone has committed to S0 Sn this way, it will not be able to bisect to a mid state other than Sn over 2, because the protocol will just be able to catch that. And this is very important because it means that the honest parties can cooperate together trustlessly, backing only one single stake. If I'm an honest validator and I see that the correct Merkle root has been posted in this protocol, I can be calm that the honest effort is on the way to victory without having to stake independently. And so I might need to make moves on behalf of the honest team every once in a while, but I will not be able to just trust myself. And this is very important for the cost analysis of the protocol. In addition, there's a novel clock management system to sort of orchestrate together all these sub-games, which I will also not go into. So basically, the result of all this is that BoLD retains all the good properties that the current protocol has, but it solves the problems that were before. So in particular, delay attacks are no longer possible. So in particular, there's a constant confirmation time to the protocol, regardless of how many malicious stakes were placed. And only one honest stake is needed instead of like K honest stakes if there are K honest parties. And finally, you can show that the honest party's total cost for participating is proportional to the number of malicious stakes. And so what this means is that this cost for participating can be totally reimbursed in the aftermath from the confiscated stakes. And there a bunch of other details, which I will not go into. This is all I have time for. So thank you.